Hello and welcome to this video. Today I'm going to present you the dAIEdge-VLab API. This API gives you access to the dAIEdge-VLab through your Python scripts. In this video, I'm going to showcase a simple application where we're going to train a model and then evaluate its performances on different targets. To begin with, I want to let you know there is a step-by-step user guide. This user guide helps you getting started with the dAIEdge-VLab API, set it up, install everything you need in order to go and start with it. You can find this on the dAIEdge-VLab documentation. So here is the overview of what we're going to do. We are going to prepare a dataset on the user device, and then we will train a new neural network with this dataset. Then we are going to send the dataset with the model we just trained to different targets. The targets will perform the inferences with the dataset we gave, and the targets will give us the raw output of the model. So these are really the values that the model outputted. Alongside, we will find a report as usual and some logs. The report on this type of benchmark, which is when we provide the dataset, are a bit less detailed than when we do not provide the dataset. When we do not provide the dataset, random input data are used, and we're also able to gather more information. Finally, we will format the raw outputs given by the targets. This will allow you to extract what were the predictions that the model made on the dataset. Then we will compute the accuracy metrics and see if everything went well. We're going to do a simple MNIST classifier. So we're going to use the MNIST dataset, which is composed of handwritten digits. And we'll train a simple neural network that will classify these images. So now let's jump into VS Code and we'll go over the code really quickly. So we'll see how easy it is to integrate the dAIEdge-VLab to your pipelines. So to begin with, we will need at least a Python interpreter, the dAIEdge-VLab API file. Now it's only available using the source file, and then a setup file that contains your credentials to access the VLab. So the code here is very simple. We take the MNIST dataset and we extract a trained dataset and a test dataset. Then we preprocess the dataset. Here we're normalizing them. Once it's done, we are extracting a validation dataset from the train dataset. Then we save the test dataset in a binary format on the disk. We will provide this dataset to the targets. Then we define the model architecture, and then we train the model using the train dataset and the validation dataset. Finally, we convert it to TensorFlow Lite and we save it on the disk. So here comes the interesting part. We select the runtime we want to use. Here we created a TensorFlow Lite model, so we're going to choose TensorFlow Lite. Then here we select two different targets, a Raspberry Pi 5 and the Qualcomm B3 Gen 2. Then we log ourselves to the VLab using the setup file. Once we're logged in, we upload the dataset we created. When we do that, we will be able to reference this dataset for future benchmark, so we don't need to push it multiple times. This is what we're doing here. Here, we're starting two different benchmarks, one on the target number 1, which was the Raspberry Pi 5, and one on the target number 2, which was the Qualcomm. Here, we are actively waiting for the results. There is a callback mechanism that you can use if you do not want to block the thread. Once we got back the results, we will format the raw output. We can see that to access the raw output, we just need to use the result we got back from the previous method and use the key raw output. We'll get back the binary file. We can do the same to get the report back and the logs. Then, by using the true labels, we can compute the accuracy that each benchmark gave back. Finally, we print all the information. So let's run this. We can start it. Once it's started, we can see that the dataset binary is stored on the disk right here. Then the training of the model starts. When it is done, the model is stored on the disk. Then the script starts the two benchmark on the two different targets and then waits for the results to come back. Once we got the results, we computed the accuracy and the mean inference time. We can see that the Raspberry Pi ran this model faster than the Qualcomm in this case. However, the difference is very small. The Raspberry Pi took 200 microseconds, whereas the Qualcomm took 260 microseconds. The accuracy is actually exactly the same. This is to be expected because we gave the same model and the exact same dataset. Because you are logged in with your credential, these benchmarks are also accessible from the website. You can also see that we've updated the way the results are presented. This is the end of this video. You can find the source code in the user documentation. Thank you for listening and have a good day.